Welcome back. We're in our unit on universal programs. These programs, I'll remind you, are programs that plan for their eventual end of use. The idea is we can't know what techniques will be available in the future and what challenges will be necessary. But we can think ahead that anybody who's using our program could still use the same basic interactions, the same logic with our program. If our program can interchange their logic with our logic, we'll be ready to change the techniques in the future, handing off our data to theirs or taking their data in as ours. This guarantees that the programs we've written with our software can continue to be used and the ideas can be recycled. We've seen several examples of this and some techniques. You might want to watch the previous videos on this, including how to program universally, how to look at some examples, and cones and co-cones. Suppose that I have a bunch of isolated data types. Today I'm just going to draw them as dots. It's not significant to know what they are, but if it helps you, you could give them names like string, integer, file, whatever types of data type you want to combine. There are two ways you might combine this. This is the version of cone versus co-cone. In the cone version, I'll remind you, the key idea is to create one universal data type which can eliminate to the ones we have. In the co-cone, we want to eliminate the ones we have and introduce one of the new kind. So let's put the two pictures on side by side. Our cone starts at the top, like a hat on top of the globe, and maps everything back to the data we want to study. The co-cone takes the data and introduces a new one. You can think of a pair and eithers, only now this might be a triple or quadruple or any number, and an either could also take many types together. Now we do the universal part. The universal part is to draw a challenger with the very same behavior and show that ours can match theirs. So now let's write down what the challenger can do. The challenger introduces their own rules to eliminate to the same data we saw in our story. But whatever they can do, we can match. We can find a new introduction from their data into ours. Therefore, whatever improvements they might have can at least be passed along to the programs that use our data type, and they don't have to update anything. They simply call the introduction rule to convert it to our new data type, and all the programs expecting our type of files will now be able to run. In the co-cone version, it's the opposite direction. If somebody can create a new data type of their choosing from the same information, then we can eliminate ours into theirs. Therefore, we can use our data in their program. The key thing is to keep these in two separate worlds. There's the cone and the co-cone. They're not simultaneously universal. And the reason they're separate is they come from different kinds of logic. The top kind of logic is based on the and, the conjunction. The bottom type of logic is based on or. These are two very related logics once we put in all the elimination, formation, introduction, computation rules, but they are in fact dual to each other. They can't be used exactly the same. You have to pass duality, such as a non-operator. Now that we've seen that and or gave us two very useful data types that happen to be universal, we might want to move to new types of logical operators. And to come up with creative names for these can be difficult. It can take a study in logic to know which logical operators are out there. Fortunately, the diagram language gives us a great head start. We've already seen one of these when we put in a single arrow. Let's update our pictures with that. So now let's jump ahead to the connection of two dots by one arrow. I'll remind you that behind this is the logic of implication. We already saw in a video how we could use this to discern the properties of two modes that could be used in a program, such as a high power and a low power mode. We could talk about eager and lazy evaluation. In that video, we favored only one picture, the top picture. The key idea was that we created a new data type that could eliminate back to the inputs or to the outputs simultaneously. Then, if any challenger had it by some other method, they would be able to convert their data type into ours. If you look at that, the style we had would favor, I claim, the lazy program. Let me try to prove it to you by putting in some equations. If I just look for a simple solution with equations, I might find it right away. What I want is that this is a commutative diagram. Beginning in this position that I'm creating, I want to go by pi a and then apply f and get the same as pi b. So that reads as the equation pi b equals f times pi a. What are some easy solutions for that when you get to choose the two pi's? One solution is to let pi a be the number 1, that is, the identity function. With the identity function composed with f, I don't change f at all, so it forces my pi b to be f. This, I claim, is the lazy evaluation model. This is where we simply store the original value a. If we want to project back to a, we just return a unchanged, the identity on a. But when it's time to compute b, we now have to actually use the f and compute it all the way down. So this is favoring the lazy evaluation. Now let's do the dual cone, the co-cone, and see what that does to our evaluation strategy. Does this favor lazy or eager evaluation? Let's write the equations. I see that the commutative diagram now wants to go across F and then iota B and get the same place that iota A would do. That's the equation iota B F equals iota A. And I want to find an easy solution. The effortless solution I could find is to let iota B now be the identity. In so doing, it forces iota A to be F. So that would be saying that the easiest case to do this would simply be to evaluate the function originally. That's the eager evaluation strategy. What about many arrows? Now our pictures are going to get a little bit more tricky to model. I'm going to look at two configurations of arrows here. Two arrows coming together at a point, and then later two arrows coming away from a point. Now this is the input data. This is used in our formation rule. So this is the entire bottom piece of our cone. So to draw this, we'll need 3 dimensions. I'll think of this as living on a plane. And I'll put that plane flat and think of my cone extending upwards. With some 3D drafting skills, this might come to mind. If you can't do this with the picture, don't worry. The pictures can be flattened, and I'll give you them in colors as well. The colors might be enough to take out the geometry. So there we have it. I have a plane flattened in space, and then I'm going to create a cone over this plane. That's my first creation. And since the data will be coming from the top down, I'll be creating elimination rules in the process. I've created a type from this elimination rule. There we have it. I've added a new term outside the plane I'm in. It's in 3-dimensional space, and I have elimination rules reaching all the data in my particular input program. So my program has 2 tasks to be done on different data that need to be combined at the end in a way that is cohesive. What does cohesive mean here? Whatever new data type I have, it's supposed to be able to eliminate out to all those pieces of data and do it in a commutative diagram. That means whatever the result is that comes out of here should be the same as composing with this white arrow and coming from here. Likewise, whatever I send over to here as data and then apply that function, it should be the same as what the middle one does. This is the nature of a commutative diagram. We can go in any direction as long as the arrows end in the same place. Now let's consider what a competitor would have to do. Remember, this is a cone. We'll create another cone, but from some other place. And the goal is to make their cone transfer into our cone. Started to look more cone-like, I hope, as well. So here we have the new cone. The new cone in orange simply maps the same data that this new contestant, the new competitor has, to the same points of the original input plane. Now what we've done is we've set up a question of a universality. We're wondering if their cone can be matched with our cone. That'll mean an arrow from their input model to our input model. In other words, we're looking for the missing introductions to our data type in yellow. We have this here as this blue line. It's introducing data at the top of our cone. It's the data that'll tell us what to program ourselves. Let's put this down in formation, elimination, introduction, computation notation. That is, let's write this with sequence. First, I need the formation rule. This is how I create the data type I'm interested in. I'm calling it pullback, and that's because I anticipate the name, which is going to match the picture. It'll be like we're pulling back from the picture we started with. Notice these 3 lines are elimination rules out of that data type. So all I needed was the introductory picture here. This F and G together were the data we needed to form this pullback data type, the top yellow dot. Let's go ahead and put the elimination rules in, since those we see in our first picture. Here they are. I've written them all gathered as one, just to simplify my notation. If I have one piece of data of this top pullback kind, it can be projected down to A, B, or C. So there's 3 different elimination rules. But there's even more. Already in this diagram, it must be commutative. We could think of this as a shaded piece of paper. And that means there's hidden equations that we can use anywhere in our reasoning. And that should be verified in our program as well. Let's add those equations in. There I have them. Pi c, our middle projection, should be equal to f pi a, then f. Likewise, if I do pi b, then g, I should also get pi c. We start to see that the role of pi c is somewhat irrelevant. It's given to us by fg and the pi a and pi b. In many of these diagrams, once we flatten them, we simply take it out, knowing that it could be put back in through the composition rules. I'll leave it in for this particular diagram. So our elimination rules are threefold along with two equations. The two solid faces are part of this elimination rule. They're the equations that govern how things work together. Once we move from there, we go to the competitor to try to make an introduction rule. Let's see what introductions we get. So let's get started with the introduction rule. We see that the introduction is going to come from a competitor that makes a cone of their own. So they'll have a data type X along with projections J, K, and L that go down to the corresponding points. I've written those as functions. Is there any hidden information we should write? Yes, there's a commutative diagram. Commutative diagrams hide equations. It's not just any JKL that they can provide us with. They need to provide us with ones that are compatible. If I go through J after and then F, it should be the same as L. And likewise, K and then G should be the same as L as well. From here, you see that L is actually not important. As long as we have those equations, we can solve for the missing L as either Fj or Gk. The key thing is we now have the full introduction data necessary to get our blue line in. We've just created our first instance of our pullback diagram. It depends on those data, and we store it inside by one of many possible tricks. Once more, we'll have choices in the engineering. Perhaps we want to pre-compute some values and store them, kind of an eager evaluation, or perhaps we want to delay the calculation somewhat till the end, a lazy evaluation, or perhaps something in between. We are not prescribing one program, we're prescribing one paradigm for a program, a technique to gather the data reliably. Anybody who does the same kind of cone will produce something that's interchangeable with any software we write to solve this. This plans for the future. This was one possible cone. What's the reverse of a pullback is if the arrows come out. And as we can see, that'll get a new name. We call that a push out. Let's flatten our pictures to give us a better chance at calculating some of these. When we flatten, what we do is we eliminate the things that can be self-explained. For example, we won't need the L, and we also won't need the pi c. So let's do this one together at higher speed. We're given f and g are functions from a to c and b to c. We're told to take the cone. We'll now think of this as flattened. I've now added the things that are in the cone. I've omitted the evaluation down the diagonal because I know that can be recovered from composition, so it's superfluous information. I've also abbreviated the pullback to simply P of FG. From here, I need to create a competitor cone. Once more, I've also eliminated the diagonal of my cone. From X all the way out to C was our L, but we can get that by simply composing J with F and K with G. They'll both give us the same diagonal. Finally, we need to put in what is our competitor supposed to do with our data type. We can see that we have no way to introduce our data type, so that's the missing piece of information. Their cone should map to our cone. And there you have it. That commutative diagram is the entire pullback picture that we need to describe a new data type. What does it mean? We'll see in the next video when we do the co-cones as well. Until next time. That's how you take care of your chalkboard.